Now let's move on to Poisson probability distribution, which we will understand that it is a limiting case of a binomial probability distribution. In binomial probability distribution, we said we conduct n independent trials, and in each trial there is something going to be, there could be a success or a failure. A group of outcomes, we branded them as success. Probability of success was remaining constant in every trial. Such trials we said as Bernoulli trials. So the probability of success in each trial was taken as P, and probability of failure was taken as 1 minus P, which is equal to Q. That was the notation we have used. Now what if n becomes large, that is n is tending to infinity? So it's a limiting case of binomial distribution, where n tends to infinity, that is the number of trials are large, and P tends to 0, probability of success tends to 0, but NP is some finite constant, NP is some finite constant, lambda. Okay. In this case, which of course means that when P tends to 0, it would imply that Q tends to 1. The probability of failure is of almost 1. So for example, let us say we are looking at the number of typographical errors in a web page. Web page consists of many characters, and if you are an expert in typing, the typographical errors are bound to be less in number, and the chance of getting a typographical error in a particular character is almost 0. But let us assume that now this is an example of a Poisson distribution where the number of trials is large, that is number of characters in the web page is very large, and P is of course probability of getting a failure, that is probability of getting a success, that is getting a typographical error is almost 0. So NP is some constant, that is lambda. Okay, in that case, what is the probability of x equal to small x? X of course counts the number of successes. Range of the random variable x is, now it is not 0 to n, you said n tends to infinity, so 0 to infinity. What is the probability of x equal to x? We have to give a formula so that sum of all the probabilities is equal to 1, so that it becomes a probability distribution. It is given by e power minus lambda into lambda power x by x factorial. X of course can be 0 or 1, 2, so on. That is corresponding to each value of the random variable, we are assigning a probability this way, right. Now is this indeed the probability mass function, or is it going to be giving us a probability distribution or not? Let us check it up. So summation of this verification, the C is that irrational number 2.7518 something, which lies between 2 and 3. Natural logarithms are talked with respect to the base C, that is the E that we are referring to here. So lambda is NP. Now what is the probability, sum of all these probabilities? X ranging from 0 to infinity, P of x equal to x. Is it equal to 1 or not? This is what I want to verify. So what is this equal to? E power minus lambda into lambda power x by x factorial, x ranging from 0 to infinity. Now this e power minus lambda is free from x, so we will pull it out. So we have e power minus lambda into sigma lambda power x by x factorial, x ranging from 0 to infinity. X is a counting number here. E power minus lambda into, if you observe carefully, this is lambda power 0 by 0 factorial plus lambda power 1 by 1 factorial, lambda power 2 by 2 factorial, which is nothing but the expansion of e power lambda. So this is e power minus lambda into e power lambda So that comes out to be 1. So we have verified that this is indeed giving us a probability distribution. This rule is giving us a probability distribution. Let's look at the mean and variance of Poisson distribution. So mean or expectation of the random variable x. This random variable x follows Poisson distribution with the parameter as lambda. We write like this: x follows Poisson distribution with the parameter as lambda. See what determines the probability corresponding to each value of the random variable? It is just the lambda. E is a constant. X we know ranges from 0 to infinity. So for each value of x, to obtain the probability, what is the thing that matters to us? It is the lambda value. So lambda is a parameter. So x follows probability Poisson distribution, P for Poisson distribution with the parameter as lambda. Mean of it is given by summation x into p of x, that is, this is p of x, e power minus lambda into lambda power x by x factorial, x ranging from, I can say 1 to infinity, because when you take x equal to 0 anyway, this term is going to be 0. So we'll take it from x ranging from 1 to infinity. But then that one turns out to be what? X by x factorial is, what is that? We can say it is x minus 1 factorial in the denominator here. E power minus lambda can be pulled out. And now what you have is x ranging from 1 to infinity. I can take out lambda also. And we have here lambda power x minus 1 by x minus 1 factorial. If you expand this, supplying the values to this, this will come out to be lambda into e power minus lambda. The bracket term is again e power lambda. This e power minus lambda and e power lambda cancel, and you have lambda, which is same as NP there, similar to the mean of the binomial distribution that we have already calculated. It's NP. So this is in expectation of the random variable or mean of the random variable corresponding to the Poisson distribution, that is lambda. Okay. Now coming to the variance, what is it we can expect about the variance? Variance for a binomial distribution we said is NPQ, and now what happens as P tends to 0, Q tends to 1, so NPQ will tend to NP, so variance is also same, is going to be lambda. Of course we can derive it, but then we will just take it. Derivation is not of much consequence, so let's look at just the formula here. So the variance is, variance and mean of a Poisson distribution are both equal to the lambda parameter value, lambda. But how do you calculate the lambda value? When you have, it is n into p, when n is the number of trials and p is the probability of success in every trial. So lambda is calculated that way.